Okay, welcome everyone. It is my pleasure to introduce the speaker of today, which is Dr. Miguel Oyuelos, who is a professor at the University of Mar del Plata in Argentina, also member of the Argentinian CONICET, and also at the IFIMAR Institute of Research in Physics of Mar del Plata. Miguel got his PhD in physics in 1994, so some time ago. And he spent with us as a postdoc 2 years back in 1996, 1998, according to the CV. He was working at that time on pattern formation in optical systems and quantum optics. He was working with Pera, Roberta, and myself at that time. And during that time, we were part of an European project, USTRACT. And so he spent some time also at Strathclyde in Glasgow and the University of Milan in Italy. And he went back to Mar del Plata, where he has been doing research in a number of different fields, most of them associated with statistical physics and nonlinear process. He's lately much interested in problems of diffusion in different contexts and the things that he's going to talk us about today. And he has also a different life, which is as a writer of novels, of short stories, and also dissemination of science, not only physics, but science in general. And some of you could listen to him last Monday on artificial intelligence, conscience in reality and fiction, a very interesting talk that we had in Diario de Mallorca. So welcome again to Mallorca, Miguel. It's a pleasure to have you here.
It's a pleasure to be here for me. Thank you very much. Okay. Transition probabilities and diffusion coefficient in interacting particle system. I will make a review of the works that we were doing in this in the statistical mechanics group in Mar del Plata. Composed, these are the members of the groups. Involved are the people that participated in the papers that I will talk about during this talk. Melina, Sampaio Puelles, and Leandro Marchioni are PhD students, and the rest are researchers. So, introduction. First, a bit of history. 100 years ago, more or less, the problem of diffusion in dilute gases was solved using the Boltzmann equation and using this Chapman-Enskog method, with which it is not simple at all to apply the method, but it is possible to analyzing the behavior of the Boltzmann equation for a dilute gas. Well, Boltzmann equation is an equation for the number density of particles. I mean, the average number of particles with a given momentum and in a given position of the system of a dilute gas. If we analyze the behavior close to equilibrium of this equation, we can see how it decays to equilibrium. This decay can be associated with different time scales that in turn are related with transport coefficients like diffusion coefficient, viscosity, and thermal conductivity. I will focus on diffusion here, but of course, the transport theory includes the other coefficients. And this, well, using all this method that I will not describe, I just mention the result. This is the result for the diffusion coefficient of a dilute gas, where this is the density. Sigma is a characteristic distance between colliding particles. For hard spheres, it is the diameter of the spheres, temperature, the mass of the particles, and this is the collision integral. It's a function of temperature. For hard spheres, it is equal to 1, and this all simplifies. The problem is what happens with diffusion or with transport in general in dense fluids. When you increase concentration and interactions become more and more relevant. This is a very old problem, not yet solved. During the last 100 years, people tried to solve this problem. This is a very challenging problem, and we do not have a rigorous theory at the level of the Boltzmann theory for dilute gases in the case for dense fluids. We have many attempts have been performed during this last 100 years. One of them, one of the first ones was the ENSCO theory for hard spheres. In that case, ENSCO obtained this expression for the diffusion coefficient. C here is the packing factor. This like the density, doesn't matter. It's directly related to the density of the system. For C going to zero, of course, we recover the result of the Boltzmann theory, this zero. Here is the packing fraction and the relation with the density. The density is the number of the volume. And here, this is the plot of the numerical results of the diffusion coefficient divided by the ENSCO theoretical result. In the ideal case, this should be equal to 1 always, but you can see here that it doesn't work well. Not even for what is called the ENSCO regime, is more or less here for small concentration. The theory works more or less or better for the other transport coefficients, for viscosity and thermal conductivity, but not for diffusion. There are many other attempts to theoretically describe diffusion in dense fluids. I briefly mentioned some of them. These ones are related with the free volume. The free volume is the volume that is not occupied by the particles. It is easy to define the free volume to calculate the free volume for hard spheres. For other kinds of particles, we have to determine an effective hard field diameter. In any case, you can define in some way free volume for any interaction, and you can, for example, consider this different proposition. This is diffusion coefficient. They can consider that it's proportional to the free volume. This works for some systems at a small concentration or weak interactions. These other two proposals, the second one or the third one here is a correction to the first one. This works for the regime of a very large concentration, even for glassy systems. This one works for polymers. And this other one, the of Rosenfeld, is not a function of the free volume, but of the excess entropy. And it was, well, quite successful for many substances, for diffusion in many substances, but also works only for high concentration, not in the low concentration regime. C and C prime are constants that have to be adjusted. There are other approaches, there are many others, but I will not mention all of them. It is a long list. I just mentioned some of them just to show you that there is not a general theory. All the theoretical approaches that are here are more or less heuristic. They include parameters that have to be adjusted, and they work for some regimes of concentration, for high or low concentration, for different substances, but are not general. So the problem is not solved in general. Our aim is to obtain general results. This is quite ambitious, but well, I have to say before anything that we didn't solve the problem. It would have been very nice, but we didn't. Not yet. But anyway, I will try to convince you that anyway, we have obtained some pieces of information that go in the right direction, that are general. How have they done that? Well, first, we start with the description at the microscopic level. The same kind of description that is used for the derivation of hydrodynamic equations. In hydrodynamics, you divide the system in cells that are small compared, these are the cells that are small compared with any spatial variation of the pressure, temperature, density, any thermodynamic quantity. And at the same time, they are large enough to contain many particles. As in hydrodynamics, we consider local equilibrium. So we can define a temperature for each cell. Local equilibrium allows us to use detailed balance. So it means that if we start with this state that in which we have N1 particles in cell 1 and N2 particles in cell 2, the size of the cells are A. And you have a transition in which one particle jumps in cell 1 jumps to cell 2, and this is the final state B. Of course, it is not necessary to specify the number of particles in all the rest. You have the transition only between these two cells. Detailed balance means that this, the probability of state A times the transition probability from A to B is equal to the probability of state B times the transition probability from B to A. We consider local interactions in each cell, so the interaction range is small enough. Or in other words, we can consider that the interactions in the walls of the cells it can be neglected compared with the interaction energy in the bulk and the grand canonical ensemble at the given temperature and chemical potential. Using this and this other definition, we define the transition particle, the transition per particle. This is the transition from cell 1 to cell 2 with N1 particles in the cell 1 and N2 particles in cell 2. This, the order of the indices indicates the direction of the jump is equal to the transition probability from state A to B divided by N1. So this transition probability, WAB, corresponds to the jump of any of the N1 particles in cell A. So if I divide by N1, I have the transition probability per particle, the average transition probability per particle. The same for the transition in the other direction. And we can demonstrate this equation. Here I skip a lot of, yes?
So can you repeat what was capital A and capital B?
Capital A and capital B are the states here, the initial states and the final state. Now I skip a lot of calculations. I cannot. Yes, you are welcome. Takes several pages to demonstrate this. We have made an expansion of the detailed balance relationship in terms of 1 over the different powers of 1 over the volume of the cells, and we can demonstrate that the transition probability from N1 to N2 of one particle is equal to this. This new is jump frequency. And this term here is the very well-known Boltzmann factor, the difference between the excess chemical potential in cell 2 minus the excess chemical potential in cell 1 divided by 2. The excess chemical potential here plays the role of a mean field potential of one particle in an environment composed by other particles of the same kind. And we have also this here dividing this capital gamma is the thermodynamic factor. The thermodynamic factor is defined as the derivative of the chemical potential with respect to the logarithm of the concentration of the number or the number of particles is the same in this case because there is the logarithm there. Or in other words, is equal to this one, to this 1 plus beta is 1 over kt, and the number of particles and the derivative, the prime here is the derivative respect to the number of particles. Well, the calculations, you can see the details of the calculation in this paper 2 years ago. That was published 2 years ago. This is the general result. Yes. No. Why?
Is this a definition?
This is a result.
So it is a description of some other process.
It's a description of this, what I described before in this transparency. The description of.
No, yeah, but what I mean is this is hopping between these three sides.
See?
With these rates that are on the next slide.
Yes. No, well, I have this. I have the local the detailed balance, local equilibrium, and from this and the statistical mechanics, and I can demonstrate the other equation for the transition rates. It can be demonstrated
For any process.
for any process. Yes. This is a general result. Yes. What? Grand canonical ensemble. Yes. You don't believe me. Yes.
How likely is it per time that I hope? Nothing, there's no time.
In this result, there is time here, this constant. This is the jump rate. This jump rate, if you consider the dilute case when the Boltzmann theory holds, the X's chemical potential goes to 0. The interactions can be neglected. Gamma goes to 1, and you have only nu. With only nu, you can connect nu with the diffusion coefficient of the Boltzmann theory. Okay. Yes.
Usually, when you impose local decay balance, usually there are several dynamics that produce the same decay balance.
Yes. Yes.
The thermodynamics,
yes.
Metropolis,
Glauber dynamics. Yes. Yes. Yes.
It seems that there is a single solution. It's a single.
This is the result. This is the result. Actually, we already also published the paper where we compare this transition rate with Glauber and Metropolis. And this describes correctly the non-equilibrium regime.
Maybe the rate is different for the different dynamics. For Glauber and Metropolis,
No. They are simply wrong. I mean, they are right because in the sense that they all give you the correct equilibrium state, but they don't guarantee you the correct non-equilibrium evolution. The time scale, what Emilio said, the time scale outside equilibrium. You need more details. Yes, you can see the details here in this paper. Well, let me tell you about the limitations of this equation before going on. There are the first limitation is that this is an average transition rate for. I mean, when you want to calculate the tracer diffusivity of one attacked particle, you need to follow that particle and see what is the transition rate of this particle in every moment. But you don't have that with this equation because you have only the average transition probability for any of the N1 particles in the set. And the second limitation is that gamma, well, here gamma goes to zero, close to the phase transition. The expansion that we use to obtain this equation does not hold close to a phase transition. And these are the limitations. Well, I want to use the time of the talk to explain, to show you what are the consequences of this equation and how can be verified and compared with known results. First, we can see that from this transition rate, we can calculate the collective diffusion coefficient and the tracer diffusion coefficient. I have to explain what is the difference between these two coefficients. They are in general different. They are equal in the when you can neglect interactions, but in the presence of interactions, they are in general different. For example, the collective diffusion coefficient is calculated when you have, for example, in the following situation: if you impose in one extreme of the system a given concentration and a different concentration in the other extreme, you have a flux, and this flux is proportional to the gradient, and the proportionality constant is the collective diffusion coefficient. Instead, if you look at a marked or tagged particle and see and calculate the mean square displacement and rush and plot it against time, the slope is the tracer diffusion coefficient. They are in general different when you have interactions. We can use the transition rates and show that the collective diffusion coefficient is this. What I showed before this. All this theory includes is useful to see what is the information at the thermodynamic level. Since we are using a coarse-grained description, we can understand this information, but not this one. The theory that does not predict anything for this transition frequency. This exponential is the usual Boltzmann factor, yes. But what is new is this quote in here, this denominator with the thermodynamic factor. Well, then the collective diffusion coefficient is does not depend on the thermodynamic state, while the tracer diffusion coefficient, without memory effects. I mean, using this transition rate, in the literature, you can see that when you neglect memory effects, I mean, when you don't consider that the transition rate may be different when you follow a tagged particle, because, for example, if you consider a discrete system, when a particle jumps to an empty site, it has a higher probability to go back because it left an empty sign behind. This is a memory effect. The theoretical result is transition rate do not take into account these memory effects. And if you neglect that, it in some situations can be done. You obtain what is called the mean field or dynamic mean field approximation of the tracer diffusion. In the case of a gas, in the case that is applied to Boltzmann theory, in the case of the dilute gas, this is also the self diffusion coefficient. Now, the tracer diffusion coefficient in a medium composed of particles of the same kind is called the self diffusion coefficient. Well, and this tracer diffusion coefficient is equal to this over the thermodynamic factor. Combining these two equations, we obtain what is called the Darken equation. Or, I mean, we can recover a very well-known result that gives you the relationship between the tracer diffusion coefficient in this mean field regime and the collective diffusion coefficient through the thermodynamic factor. This is known since 1948. but we reproduce this result following a completely different path. Moreover, we have more information here. Here we have two equations. Here we know how the thermodynamic factor affects the tracer diffusion or the collective diffusion. We see that it does not affect the collective diffusion coefficient. And this is the new information. Well, we have checked this theory using very simple numerical simulation in a discrete system in one dimension, where we put particles that jump with the transition rate, as we show in the previous transparency, and use different excess chemical potentials. For example, the circles here correspond to soft core interaction. Means the density is defined as n over a maximum possible number of particles in each position. It means that there is a maximum value of rho equal to 1. For rho equal to 1, the tracer diffusion or the self diffusion goes to 0, because of is this similar to the exclusion principle, Pauli exclusion principle, what doesn't matter. The excess chemical potential in this case is 1 minus rho. When rho is equal to 1, this is equal to 0, it means that the excess chemical potential goes to infinity. When rho is equal to 0, there is no interaction, the chemical potential is 0. We can calculate this tracer diffusion coefficient. Well, the lines are the theory and the dots are numerical simulation. This is the collective diffusion coefficient that remains constant against concentration for constant nu. This is an effective interaction that reproduces the statistics of bosons. If instead of minus you put plus, you take this other result. This is also just to check the theory. We proposed excess chemical potentials that behave as power of the density, obtained also numerical results that of the diffusion coefficient of the tracer and the collective diffusion coefficient that matches the theory, the theoretical prediction. This also was published here in the last year. What happens with memory effects? In general, they are included in what is called the correlation factor F, the diffusion coefficient. Now the self-diffusion coefficient is written in terms of the diffusion coefficient of the Boltzmann theory for small concentration divided by the thermodynamic factor times this correlation factor. Darken equation does not hold in general because of F. Transition probabilities, as I wrote them before, can be separated in these two parts. This new includes the microscopic details, and all this that is what we have derived is at the microscopic level, at the thermodynamic level, no? Because it depends on the chemical potential. As I said before, if you consider the case of a dilute system, all these factors, all this term is equal to 1, and you have only this jump rate that can be connected with the diffusion coefficient of the Boltzmann theory. This result suggests that we can also write the diffusion coefficient, the self-diffusion coefficient, as a product between this 0 from the Boltzmann theory times a function that includes microscopic at the microscopic level. The microscopic level, I mean the size of the particle, the mass of the particle, etc., appears only here. And this is a function that depends on the thermodynamic state. This can be, we propose this inspired or motivated by the form of the transition rates as an hypothesis, and we can check it numerically. To check this hypothesis numerically, we have done the following. First, we consider a continuous system at small concentration. We need D0 in the system that is defined in this way. We consider our system, we're interested in the red particles. The small particles are the medium in which the red particles move. And they produce, using the Langevin theory, they produce a stochastic force and a damping force. That are the amplitude of these forces are connected through the fluctuation dissipation theorem. And both can be completely specified if we specify the damping time that is equal to 1 over the friction coefficient. So if the damping time is equal to, is very large, it is the system will behave as in the case of the Boltzmann theory, as if it were in vacuum, because the effect of the surrounding particles is almost cannot be noticed if the damping time is very large. They don't how to say it, reduce significantly the velocity of the particle when it moves without colliding with other particles. Instead, if the damping time is small, these red particles behave as if they were described in the Langevin theory, and they should diffuse with the Einstein diffusion coefficient. We have these two extreme situations, very large or very small damping time. In each case, we have a theory that describes the diffusion coefficient. Einstein theory or Boltzmann theory. And well, and this equation is, this relationship is justified as follows. You can consider that the flux of particles, the particle current has a resistance that is proportional to 1 over the diffusion coefficient. This resistance of a red particle, the red particle may collide with the small particles or with other red particles. So the resistance produced by both kind of particles is in series. We have to sum the resistance of the two kind of particles. This is the sum of these two resistances. Well, we can check this equation. We can calculate the diffusion coefficient. The asterisk means that they are adimensional quantities. Doesn't matter how the units are eliminated. Against the damping time, from 10 to the minus 1 to 10 to the 3. The line is the theoretical curve that comes from this combination of these two well-known theories, and the points are, the crosses are numerical results. For pseudo-hard spheres, are almost the same that hard spheres, but with a continuous potential. And this is for the Lennard-Jones potential for temperature equal to 4, the same. From small damping time to large damping time, we have that this relationship is satisfied. We obtain in one extreme, as I said before. For large damping time, we have here Boltzmann theory. For small damping time, we have here in the other extreme the Einstein theory. We reproduce one or the other diffusion coefficient. And in the middle, we have this that is given by this equation. Okay. In this way, we have the diffusion coefficient for small concentration in this system. Now, if we calculate the diffusion coefficient for pseudo-hard spheres with noise, of course, it is different for different noises, for different noise intensity, or mean, for different damping times. The red crosses are for damping time, a small damping time. The diffusion coefficient is smaller because the particles can lose their velocity very quickly. And for larger damping times, we have larger diffusion coefficients. Okay, now I am coming back to the hypothesis that I mentioned before, that d over d0 is a thermodynamic function. This is the hypothesis that we are proposing. So if d over d0 is a thermodynamic function, and given that the equation of state does not change when noise is added, this is something that also can be proved and checked numerically. The equation of the thermodynamic state is not modified by the inclusion of noise or inclusion of a Langevin thermostat. Then d over d0 does not change when noise is added. D over d0 must not change, and this is what we checked. Sorry. A function that depends on the thermodynamic state. Yes. The thermodynamic state does not change. So for different values of the noise, different colors here correspond of the damping time between 0.1 and 10. This is for pseudo-hard spheres. This is for the Leonard system, and more or less they collapse in one curve. So in this way, we can check this hypothesis. This was published a few months ago. Also, another consequence of what I said before. I told you before that the collective diffusion coefficient does not depend on the thermodynamic factor. I mean, it does not depend on the thermodynamic state. The intrinsic diffusion coefficient is equal to the collective diffusion coefficient in solids. It's just a different name that is usually used in solid diffusion literature. And here we wish to compare with some experimental results. The information that this diffusion coefficient is independent of gamma allows us to propose a simple approximation for the intrinsic diffusion coefficient. First, the most simple approximation will be without this exponential term. In that case, we are using what is called the Vegard law or Vegard rule, in which when you have a mixture, I didn't say that the diffusion in solid, I mean diffusion in a binary alloy, solid composed with a mixture of atoms, usually metallic atoms, that diffuse through the substitution mechanism. I mean, you need a vacancy for the particles to diffuse. This is the most important mechanism when particles are of similar size. Okay, well, I was saying, forget for a moment of this exponential term. NB and A have the molar fraction of species A and B. I mean, these numbers go between 0 and 1. DA0 and DA1 are the intrinsic diffusivities of species A for a molar fraction 0 and 1. If you neglect this exponential, you have simple, in logarithm scale, a linear approximation for the behavior of the diffusion coefficient, of the logarithm of the diffusion coefficient in terms of the molar fraction. This linear behavior is corrected by this nonlinear term here. This is a possible deviation from the Vegard rule, a nonlinearity in the activation energy. The activation energy is the migration energy plus the vacancy formation energy, which each time a particle jumps has to migrate and also has to find a vacancy. Well, this simple approximation can be used to describe some experimental results. It's just a parabola in the logarithm scale, in vertical axis of the diffusion coefficient or the intrinsic diffusion coefficient against a molar fraction. This data was taken from this reference, and now these axes have units. Migration, well, we wanted to know what is the cause of this curvature. In general, always there is a curvature in this direction, negative curvature. And we found that the main factor that produces that curvature is migration energy, but it's not very important. Using lamps, we can calculate the migration energy from one point to a vacancy. This blue particle is jumping in a medium composed of a mixture of nickel and palladium. We can obtain the effective interactions using lamps and calculate the migration energy using a special method. This was published also recently, a few months ago. And we can see that the migration energy does not follow a linear law, but is smaller, and a smaller migration energy for intermediate concentration is what gives you a higher diffusion coefficient for intermediate concentration. Okay. Now, an extension to quantum particles. What I have told you before is always a classical system of particles that jump between cells when you divide the system in small cells, and also the jumps are in normal space. But now we can consider jumps between energy levels. And almost the same calculations can be applied in this different context, where we consider quantum particles, but non-interacting quantum particles. No, they are not interacting. But we also have something that is equivalent to the excess chemical potential in this quantum context. That is the departure from the ideal classical chemical potential. We define what is the chemical potential. We define it as the ideal chemical potential in the classical case, plus mu q that includes the quantum effects. This is the departure of the chemical potential with respect to the classical ideal chemical potential that is given by this, by the logarithm of the concentration. GI is the number of states in level I that is proportional to the volume. I am considering a volume of non-interacting quantum particles that are fermions or bosons. Most simple quantum system. They are each energy level is composed by many quantum states, because the number of the states is proportional to the volume. And in if the number of particles, the average number of particles in level I divided by the number of states is the well-known distribution of fermions of bosons. Now combining these equations here, we obtain an expression for the this mu q, that is, as I said before, the excess chemical potential in this context is equal to this for fermions or bosons. And now, if we replace this expression for mu q in this result that can be demonstrated, if you believe me, if not, Well, the only thing I can do is suggest that read the papers, and of course, if you have anything that is wrong, it would be very useful for us. But in principle, we consider that it is correct. And we can check that it is correct, because if we replace this here, we obtain this expression here. Many factors are here are canceled, and we obtain this. And this is a very well-known transition rate for gas of fermions of bosons with this factor 1 minus plus the number of particles here divided by the number of states. I mean, for example, if they are fermions and the level is full, it means that N2 is equal to G2 and the transition rate is 0. We cannot go the transition rate for going from level 1 to level 2. If level 2 is full, you can't go there because of the Pauli exclusion principle. Instead, for bosons, we have the plus. There is not an easy argument as for fermions, for bosons, but anyway, this is well known because if you put this transition rate in the master equation for the gas of fermions of bosons, and you calculate the equilibrium state, you obtain the result that is expected, the distribution of fermions of bosons. This is an heuristic result. Well, here we demonstrate that this is through this result, we can obtain this that is already known.
What is the prime?
The derivative with respect to the number of particles. Sorry?
Right. So you say that plus minus N2. But in the case of bosons, we have the plus, right?
Yes.
The rate N2 is the number of particles in the second, or raising in the second phase.
Yes. In the destination level.
So why does the complete rate into a state depend on how many particles are already there?
Yes.
Particles are not there.
Well, this is the exclusion Pauli principle. No, for bosons, there is also, well, the inclusion principle. I don't know how to call it, but some people call it the inclusion principle instead of exclusion. But well, yes, there's sorry. Yes, in some books you can find a statistical interaction is called, or effective interaction, but it's actually a statistical effect. No. Well, so we found that we already know, we knew before that the transition rate depends on the number of particles in the destination level. It does not depend on N1, the number of particles in the original level. Now we can go back to the equation and look at what happens if we consider that the transition probability depends only on the destination level. I mean, on this term, but it does not depend on this term in red that depends on N1. So I impose the condition that this term should be equal to 1. If I impose this condition, and I can solve this equation and obtain this for the mu q, that corresponds to what I showed before here is the same. This corresponds to the statistic of fermions or bosons. So we can consider this as an alternative way to obtain the known statistics of fermions and bosons. I mean, if you say that the transition rate depends only on destination level, you can obtain the statistics of fermions and bosons from this equation. Okay? Well, I want to tell you about one last result that is, I don't know how to say it, rather speculative. If you Well, let's say it. Sorry, yes. Onions.
Yes, that says that for anions should depend on the initial level. The diffusion should depend on the initial level.
May.
Different from fermions and
Yes, yes.
If you assume the diffusion rate does not depend on the stage on the original level, there's only two possible materials.
Sí, fermions and bosons.
You have another thing that must depend on the
yes, also on the original level.
On the original.
Yes.
So that's it.
For exotic statistics. Yes. Yes. Yes.
Okay, depends on the arrival, but not on the point you are coming to. There is such a dependence.
No, I don't know that. I don't.
Yes.
Yes, I don't know why. This is I don't know. I don't have a question. I mean, but this is nothing new. And I mean, these transition rates are well known since a long time, and you have always that it depends only on the number of particles in the destination level. But this is the energy difference between the two the levels. Yes.
Let's go with speculation.
The speculation is as follows. If you consider the transition probability depends on destination level, you obtain fermions and bosons. And now it is a more or less natural step to consider what happens if you invert time. If you invert time, you have transition rates that depends only on the original level. Okay, what happens in that case? You obtain exotic statistics, different statistics than fermions and bosons, but you obtain this. Transition probability depends only on origin level. I mean, and now this term should be equal to 1, and these are the exotic statistics that appear. We call them in a paper Eucons and Kencons. Doesn't matter the name, but if you look at it is slightly different because you have a minus sign here and here not. The solution of this equation gives different mu q, and the mu q allows you to calculate the statistics, the average number of particles. And it looks the same as the fermions and boson statistics inverted, and also with the sign here changed in the sign of the exponent. And it turns out that the exotic statistic with the plus sign, with the minus sign looks not very well because it can give you a number of particles, a negative average number of particles, if the energy is larger than the chemical potential. So for the minus sign, I will not speak very much, but should be considered that the energy should be always smaller than the chemical potential. But with the plus sign, what is interesting is that these statistics can be used to describe dark energy. Here comes the speculative part. Dark energy, yes. So, let's see. If you look at the literature in cosmology that want to explain or describe dark energy, the usual way is to include an interaction term in the Lagrangian, an interaction term in a scalar potential, in the scalar field, I mean. And there are endless possibilities. and there are endless variation, is a useful exploration work that it was done during the last 20 years, more or less, to try to understand how dark energy can be described. The main point is that dark energy has negative pressure, and this is necessary to explain the accelerated expansion of the universe observed. In cosmology, people use this barotropic parameter, the ratio between pressure and energy density. The observed value of W, also it's called the cosmological equation of state. The observed value is similar and greater than -1, is negative. Because in this moment, the universe is dominated by dark energy, and dark energy has a negative pressure. If you calculate the barotropic parameter, this W, for an ideal gas of Elkins with this statistic with the plus sign, you obtain a W equal to -1. So it can be a description for dark energy because of this coincidence between W for W. Well, these are some publications. I mean, I think that the most interesting is this last one of the last year, in which we talk about this exotic statistics to describe dark energy. This is an alternative way to describe that energy. In this case, you don't need an interaction part in the Lagrangian, an interaction term in the Lagrangian. You use the free Lagrangian, and and you obtain a negative pressure due to these statistical effects of these exotic statistics. So you can take it as I don't know, an exploration game that for us has some nice features. First, it is simple because
general form of because it's okay, but it is, we give you this legal potential was game. The result reproduces the dark equation and those collectively that's independent of the dynamic factor. I like to mention that this is consistent with current approaches such as the evaluation method. There's people that also consider that the collective prediction coefficient does not depend on the mechanic state. Meta simulation check predictions, also numerically from that is we shown that the experimental results of the diffusion results are consistent with theory and
Thanks, Miguel, for taking us back to fundamental questions. There have been a number of questions, but yes.
About the last thing you just explained us. So if just to check if I get it right to take it home. So you are saying that if there are particles, so if there are there's quantum particles which are interacting, not interacting. Okay, because the interaction comes through the statistics. Okay, or yeah, okay. So if in that case, if the transition probabilities depends on the original state, not on the final state, you get this result of the negative pressure. Okay, just to check that I got it. So, but no interaction, because in the first part there was interaction when you got this formula. Okay, exactly. In the quantum part, you get it just from the statistics. So, yeah, okay.
More questions, comments, David?
Does this have to do with time reversal? Because you mentioned it. But you assume in the beginning that you're in equilibrium, right? So in equilibrium, there should be no distinction between past and future. So okay, I mean the mathematics is clear. It's just the interpretation which I don't see. But okay.
Yes, about the formula for the transition rate. I understand it because from the tail balance you can obtain the ratio between transition rates, no? But how do you determine the constant nu? You need more microscopical details, right? You cannot obtain that simply from the tail balance. Okay, so that depends on your particular model or whatever. Okay. Okay. Okay.
I still haven't understood. Could you please write the WN1 and 2 in terms of WAB? Do you have at the beginning? Could you define these two? No. Yeah. And here, in a way, you're assuming that you have two functions, one WAB, WBA. But you're assuming that they can be written as a single function, WN1 and 2. Well, that's a restriction on the possible rates. I think that you're using the same function, WN1 and 2, and WN2 plus 1 is the same function. Still not good.
It's like It's like assuming that all the patches are the same, no? Like are identically distributed. Like it's an homogeneous system, so all the patches will behave the same way.
More questions? And what about Sally's statistics? Sally's, how do you get Sally's statistics? Okay, if there are no other questions, Miguel will be here until Friday. So if anyone wants to talk to him or discuss with him, he's in the last office in this corridor. Thanks again, Miguel.